Wait until I'm getting the okay.
Yeah. Welcome everybody back after the coffee break, refreshments, after the rather exciting starting session. I don't know whether it's exciting for me. To me, it was very exciting like this. Things were very late and a bit messed up in the beginning, but great to have everybody back. So now we're going to the hardcore stuff, the atom interferometry, and Enno is going to present it.
Okay, yeah, well, thank you. And I'm happy to be here in Crete, in Archanis. I will give, together with Alexander Friedrich, a 4-session lecture on the introduction of atom interferometry. I gave a similar lecture during my postdoc times in Ulm. Now I'm in Darmstadt. I don't think you need to remember everything that's on the title page, but in case you want to shoot me or Alex an email and have a question afterwards, just feel free to do so. As well, just ask while I'm giving this lecture. Now, I do have some slides prepared, but I won't be giving a slide presentation. It will be almost like a Blackboard style, but I just want to give you the overview over those 5 lectures that we are planning on presenting to you. The first lecture, so today, will be on atom optics. And of course, that's a broad topic. I will only talk about one specific thing, and that's Rabi oscillations. Some of you might know Rabi oscillations, but it is Rabi oscillations including the center of mass motion. I will explain that later. Later on today, we will talk about the structure of atom interferometers, just a specific type of atom interferometers that we are talking about, but of course, these concepts can be generalized to other interferometers as well. So we will talk about light pulse atom interferometers. And tomorrow morning, I will give some basic examples. We will see that, what determines the contrast of an interferometer. Can we measure accelerations with an interferometer and something like that? The final 2 lectures will be given by Alexander. He will talk about a perturbative description. So everything will be theoretical in some sense, but I also have some slides with some experiments and some perturbations. He will show you, for example, how gravity gradients, how nonlinear potentials enter the phase of atom interferometers and how rotations work. And then we will talk about spatial fringes, some of those pictures that you already saw and effectively also heard this morning. Now, okay, now somehow my animation is gone. That's fine. No, I know what. That's the wrong presentation. Yeah, okay. But that's fine. Just a second. There you go. So it should be lecture 1. Exactly. So actually, I wanted to give that syllabus afterwards, but let's talk about optical interferometers. So you all know optical interferometers. Wolf talked about a single photon interferometer. What do you need? You need an input beam. You need optical elements, beam splitters and mirrors, and you need some type of detection. And of course, you need something that shifts the phase and where the propagation. And of course, they are very useful, and you all know that interferometers can be very useful. Now, if we want to transfer this concept to matter waves, we need each of these 3 or 4 things to basically map into the matter wave domain. Wolf did a wonderful job this morning in talking about the input beam, the sources. How do we generate cold atoms, ultra-cold atoms, or Bose-Einstein condensates that can be used as an input? And I will talk about this beam splitter today for optics, matter waves. Now, this is, pictures as you always see. Some people call them stack plots. This is just a photo of a Bose-Einstein condensate. It's just sitting here in this position. Just a picture. Now, if I wait for a time, and take another picture. It's still sitting there, maybe expanding, but it's still sitting there. Still sitting there, so it's apparently pretty boring. So what we want to do to build an interferometer, we want to have a single atom, or a Bose-Einstein condensate for that matter, to move in a superposition of two trajectories. And for that, we need to manipulate that. And most of the times, and especially in light pulse atom interferometers, you do that by interacting with light with it. Here we apply such a beam splitter pulse. And after that, you see somehow two clouds emerging, and they're moving apart. And that implies this beam splitter has inserted or applied momentum to the atom and created a superposition of two different momenta. So those clouds move apart. And now we apply, again, a light pulse that acts as a mirror, that inverts both momenta and redirects both momenta so that they meet. And now, to really come up with an atom interferometer, we need a final atom optical element that's a beam splitter. And here we mix them, and then you see all those nice little spatial fringes. So there's really, truly atom interferometry. So actually now I wanted to explain to you what we are all doing. So we are going through this step by step. And what I'm going to start with is now with atom optics. Okay, good. So let's start with that. And what I'm going to do is I'm going to develop these Rabi oscillations, including center of mass motions, like from an atom optics perspective. And I will do this here on this PDF, and I will share that later on with you, but also feel free to take notes. So it's like a conventional lecture, just this is my whiteboard, it's digital. So we will start with atom optics, and we will start with dipole interaction. I hope you can read that. If it's probably too small. Too small? No, okay, I can zoom in a little bit. Okay, dipole interaction. Okay, and we now think just in analogy to a classical dipole with an electromagnetic field. And how does this type of interaction energy look like? So let's draw it. So we have something like a dipole here. By the way, my handwriting is not that nice, so I'm going to type most of it, but the equations, unfortunately, will be in my handwriting. In case you have problems with that, good luck. No, feel free to ask also questions. So this here is little d. That's a dipole. And of course, we have this dipole interacting with some magnetic field that's here sitting here. This would be the electric field. Now, of course, it's also a vector. How does a classical dipole interact with the field? Well, we have an interaction energy. And this dipole interaction energy is minus the dipole moment times the electric field. And that's it. Now, you know that maybe from classical electrodynamics. Now, in quantum mechanics, what we are doing, we are not really going into quantum optics. We are not going to quantize the electromagnetic field, but the dipole itself. So we assume it's a classical electric field that interacts with a dipole. And this dipole now is, I just make a hat to denote it's an operator. So of course, you can derive that from a very sophisticated model. So in principle, you can just put in a nucleus, just a proton, let's say, an electron, and have them interact through Coulomb interaction. And usually how you would do that, you would introduce the coupling a coupling through minimal coupling, including a vector potential and so on. Then you get, of course, a more complete description of all of that. However, in the very end, when you make some assumptions, basically dipole assumptions, where you assume that the wavelength of the light is way larger, or the spatial change of the light is larger than the dipole itself, and that would be the atomic distances, you can basically or effectively just assume that an atom is described by such a dipole. And so in principle, the original model that we're using is we just represent this dipole as having here the nucleus, here somewhere the electron, and then, of course, we have this dipole moment, and this classical dipole moment would be written as the charge and the distance between the two of them. And the distance between the two of them already tells you that it has something to do with the internal structure of the atom. If you just, in quantum mechanics 101, solve a hydrogen atom, you're solving the radial Schrödinger equation. That implies that you're talking about the distance. So this dipole moment effectively is connected to the internal structure of your atom. And so we can, yeah, exactly. So we just write this now. The dipole moment is determined by charge and distance between electrons and nucleus. And that, of course, has implications because it has implications on the internal dynamics that defines the energy structure. And it has implications on the, and that also implies that we will decompose this operator now in internal degrees of freedom. So that means we will write it in the state space of the atom. Okay, for a two-level atom, and in the following, we will just talk. I'm a theorist, so it's too complex to talk about all this energy structure and so on. We just talk about a two-level atom for the moment. So we have an atom, and this atom has two states. It has a ground state and an internal state, ground state and an excited state. And of course, some energy difference between the two. I will call that omega atom. This is omega excited, and that is omega ground state, which maybe should be black anyways. And so for this two-level atom, we will just decompose it, and we will, and it turns out that this dipole moment is off diagonal. So if we now write this in terms of eigenstates of the internal motion, we have some transition elements, DEG, call it like that. And we have now the transition from the ground to the excited state plus the Hermitian conjugate going from the excited to the ground state. And you see exactly what this operator does. It's just expanding this operator in its internal degrees of freedom of the atom. And effectively, that's how we see how we can talk about transitions. And Wolfgang Schleich is going to talk about that, I think, tomorrow, if I remember correctly, from a different perspective. I will also assume that this D is real. You can also say it's complex, doesn't really matter because you can play with phases later on, but just that you know. So, so we now know how to describe the atom in this little interaction energy, but we still need to talk about the electric field. Now, we will assume a classical electromagnetic wave, but now, and so far everything is pretty much standard. Probably some of you or a few of you already know it. But when we talk about the electric field, I will now assume a monochromatic plane wave field that is being chirped. We will see later that this chirping is important if we have gravity, because we now take the motion of the atom into account. It's also important that it's a plane wave and not only oscillating in time, because we want to build a beam splitter where we transfer momentum and the atom moves along two different trajectories at the same time. And we need the spatial dependence of the electric field for that. So let's talk about the electric field. And for us, it's a chirped plane wave. So how does that look like? Well, a chirped plane wave, also not that difficult. You can say the electromagnetic field, it's a vector, depends now on position. I'm just working one-dimensional, and because I'm coming from I'm coming from gravimetry. Z, that's along gravity. And then we have some field amplitude. It's just a classical amplitude, E naught. And now we have e to the I, phi, z, and t plus hc. Now, that's the amplitude. We already talked about that. Now, what's this phase that I just gave? Well, and it is exactly what you think it would be. It is just phi index L. That's just an offset phase. Then we have the wave vector of the light, kz, minus omega t, plus k alpha t squared over 2. So this here would be the frequency. This here is the wave vector. This is the rate of change of our frequency. This is what we call chirping rate. And it has the units of an acceleration. So this is chirping. Okay, and yeah, and that the first thing is just an offset phase. Mm-hmm. Of course.
Okay, questions. For example, where is the vector nature on the right-hand side of the dipole? Just
because I forgot that, that's a perfect question.
Everybody's asking a question, please.
Okay, yeah, everybody, please. Okay, good. So we have now a plane wave that depends on Z. And Z now, because if you perform this approximation that I talked about, or this derivation, I'd rather say, where you talk about the position of the atom or the position of the nucleus with respect to the position of the electron. And yes, please. What I'm writing here? Chirping rate. K alpha t squared over 2. So it is a quadratic in time. That's the main message. K alpha is just for nice scaling. And t squared, that's basically the frequency is changing in time. And so the frequency is increasing in time. I'm not good in whistling. So it's a chirp. And that's exactly what is now reflected in this equation. Yes?
Frequency is changing linearly and then it's multiplied by t, or?
So effectively, there's a factor of 1 over 2. Usually you would integrate over the frequency, or rather say the instantaneous frequency is defined as the derivative in time of this phase phi. Okay, that's the instantaneous frequency. We will later, by the way, also come back to what Wolf was talking. Yes, so it's increasing. The frequency is increasing in time linearly in this approximation. We will also come back to what Wolf talked later, earlier, because we were talking about detunings and stuff. And we will see this directly when we move into a different frame or into a different picture. And I will do that explicitly because it also simplifies our calculations, you know, with this magnetic force and so on, because you also turn that into a frequency, into a Doppler frequency. Okay, so now the cool part is we have something that says E to the ikz. And what does that mean? So I was before those questions, I was going to say we evaluate the electric field at the center of mass position of the atom. That now denotes the position of the atom. And that is important because now it is exactly this spatial dependence that exerts the momentum on the atom. And we will see that because the position dependence, yeah. What's going on? Dependence will basically lead to a momentum transfer. And we will see that by the following little calculation. So let's just say we have this e to the ikz and have this acting on a momentum eigenstate. Okay, what happens? Well, let's just use position representation. And e to the ikz acting to the left is very easy. It's just a phase factor. So it is just e to the ikz, now without a hat, no operator, zp. And now we also go, we have the momentum eigenstate in position representation. I don't want to worry about square roots of 2 pi. Let's say it's just proportional to e to the ikz and e to the I pz divided by h bar. But this is nothing if we just combine those two exponentials. That is I to the h bar k. So of course my h bar and k now look alike. H bar k plus p divided by h bar times z. And that is nothing but the momentum eigenstate shifted by h bar k. So we see that the wave vector, the spatial dependence of our electromagnetic field actually shifts the momentum. That's called a displacement operator, and you're going to love it throughout this lectures that we are giving anyways. So what we see here is that e to the ik, there you go, this guy here corresponds to just a shifted momentum. We can even play with that a little bit further. We can just now work with the following relation. I just need that later. That's why we're doing it here. E to the minus ikz, that is doing effectively the opposite. A function f of p hat and then e to the ikz. What does that do? And here's also an operator. So let's just have this, all of this acting on a momentum eigenstate. And if we have this acting on a momentum eigenstate, we know it shifts. So it's e to the minus ikz and f of p hat, the operator acting on p plus h bar k. So we can now have this function acting on here. So we just need to evaluate that function at a shifted momentum. So we can just write this as e to the minus ikz times f of p plus h bar k. Sorry, I just write it here, p plus h bar k, and then f of p plus h bar k. But now I know how this here acts because this just shifts the momentum back. So I'm just back at my original momentum. So I just can write this as f of p plus h bar k acting on the momentum eigenstate p. And we can write this now as p hat plus h bar k, momentum eigenstate p. And what we now demonstrated is that if we sandwich a function that depends on momentum, we see that just the shifting, that this function is shifted in momentum. Okay? Yes. Why? You will see later. And we will use that relation because we will play around. And actually what we will observe, it is we will have, when we have this atom interferometer, we will have on one arm the atom propagating with increased momentum. And this here is just, the propagation, if you think about F as being describing the time evolution along one arm, it has an increased momentum on one arm and not increased momentum on the other arm. And that's reflected, and that's why we need this relation. I saw another question. No threat. Okay, good. Perfect. So now let's think about this from a microscopic perspective or so. We see now here that the electric field that you still see up there has a Hermitian conjugate part. And if we were to work in a second quantized version of what I'm doing right now, so making heads about the electric field in one way or the other, you would observe that actually the one part of this electric field is associated with photon absorption, and the Hermitian, that would be e to the minus, that would be photon absorption, yes, and the Hermitian conjugate part would be associated with photon emission, because one would have a creation and annihilation operator. I'm not going to go in that, but in principle, that's the, let's say, quantum physics description behind that. And if you use that, you see that when the photon is absorbed, you get a positive momentum kick, e to the ikz. If the photon is emitted, you get a kick in the opposite direction. And that just reflects momentum conservation. And that's close to the radiative force that we heard earlier this morning about, just, you know, having from multiple directions and so on. I'm just talking about one direction. Okay, good. So let's just write down the Hamiltonian, just to describe the whole thing, the Hamiltonian of our atom interacting with light. And that Hamiltonian is the following. And now I just wrote down the interaction. I now want to take center of mass motion and internal degrees of freedom into account. And for that, we just say that, you know, H, the Hamiltonian, is H external. So this is the Hamiltonian that describes the external motion of the atom. I will write down that later anyways. Plus the internal energy, H bar omega in the excited state times the projector in the excited state, plus H external plus H bar omega in the ground state times the projector in the ground state minus what we talked about so far. Okay, that would be the whole thing. Now, what I didn't say is so far, or what I didn't specify, and we will just talk about gravity. The center of mass motion, the motion of the atom, center of mass motion, is included in here. So it's a different Hilbert space. It's not the Hilbert space that acts on the internal degrees of freedom. And what we observe is the following. H external is equal to P squared over 2m plus m times g times z, just for the sake of simplicity. Okay, so we just say, we turn off our trap, we have the atom, and this free atom now interacts with the light field. Okay, what do we do now? Of course, that's nice to write down, but it will be more convenient and very close to what Wolf has been doing this morning to just go into an interaction picture. We have an interaction. We just move by a unitary transformation in an interaction picture that just removes the first two parts here. So that removes everything up here. Of course, I wanted this guy, okay? That just removes these two contributions. Okay? What's yellow? Everything that's yellow. Everything that's yellow is removed by just applying this, a textbook transformation into the interaction picture. What happens if you go into the interaction picture at this stage? You will observe the following. You will, into interaction picture. With respect to the first two terms. And you will observe that the electric field now is evaluated at the position of the atom in the interaction picture. So E field evaluated at, and we will now see, it will have a phase and we just go into this interaction picture. So we have just phase of that depends on time that is written. This operator has to be written in the interaction picture. And how does that interaction picture look like? Well, it's a linear Hamiltonian, so it's fairly easy. We can write this as Z in this interaction picture is equal to Z plus P hat times T over M minus GT squared over 2. Okay, so what you observe now is, okay, this here is, it's almost like a classical trajectory. The position is depending on the momentum in time, and it changes because of gravity. In this particular interaction picture, it's like being in a, let's say, freely falling frame or moving with the center of mass motion. And we just do this by unitary transformation. Yes?
I just have here about the H, the Hamiltonian, right?
Yes.
Usually I'm used to, okay, having H0 plus H external. This is not the same. You multiply basically the
Yes, exactly. So exactly. So in general, just that you know. Exactly. We have 2 degrees. So we're talking about interference, and we are interested in measuring gravity later on, for example. So we want to learn something about the motion of the atom. And that's encoded in the external degrees of freedom in the center of mass motion. So in principle, we are working in a Hilbert space that is the product of the external degrees of freedom, P squared over 2M plus mgz, and that's effectively what my hat external is acting on. And then we are having here the internal degrees of freedom, and that's our internal Hamiltonian. And here, this one, sorry, is just E and G for a 2-level system that describes the relative motion between electrons. And so now we have the product of the 2, and of course, a way larger state space. Yes? Exactly. So that's the cool, and that's now the point that I want to make. Actually, D acts on the internal degrees of freedom. But scalar product with E, the way you usually write it down in most quantum optics textbooks, E is just, if you just say it's a classical field, it's just a time-dependent function. But now what we are saying here, this here depends, because it's a position-dependent field, it acts on the center of mass degree. It acts on the external motion. And that's why the interaction energy actually couples both. And we are going to use that. We are entangling the internal state to the external degree of freedom, to the motion of the atom. Okay, so that's the first part. The second part is, of course, the dipole operator. I'm sorry, yes. No, it's not done by the chirp. Even without gravity, we would have that. Why? And now I was about to explain that mechanism in a second. But effectively, it's the following. You're sitting here. The atom is in the ground state. Okay? I absorb a photon. Get excited. The photon was coming here. Afterwards, there is no photon. But the photon has momentum h bar k. So what has to happen is that the whole atom gets a kick of h bar k. So you know, whenever the atom is excited, the atom has gained momentum h bar k. Whenever it was excited and emits a photon, it has lost h bar k. And that's why you have entanglement between the two. Okay, so the dipole operator in this interaction picture just oscillates with the frequency, with the atomic frequency difference. So it is just D in this interaction picture also depends on time, and it is EG vector coming from G going to E, and now it oscillates with e to the I omega atom times T plus the Hermitian conjugate. if you think about that, it's just, it's coming from these projectors and h bar omega e times projector on the excited state or the ground state with respect, that just gives rise to this difference. And that means that especially that this transition is oscillating with that atomic frequency. Okay, so let's write down now the Hamiltonian. And when you think about that, the electric field has two contributions. Is the sum of two terms, and the dipole is. So if we multiply that out, we in total get 4 terms. And these 4 terms now, or we find this Hamiltonian. And the Hamiltonian is the following in this interaction picture. It is minus dEg times E naught, and that's a scalar product. And now you have this direction of the atomic dipole, this transition moment, and the vector of the electromagnetic field. That's where the polarization of the electric field comes in. Now, if you multiply the two, it's a scalar thing. And we like to express everything with the dimensions of an energy. We like to express that as a frequency. So let's just call this guy, and I use h bar omega Rabi divided by 2. Now, what else do we observe? Well, we observe now, yes? You don't have to do that, but if you it's effectively because we want to call a pi-half pulse later on. You could also have defined the electromagnetic wave with a cosine if you like, then also this factor of 2 comes in. But we will see later on that if we call a beam splitter a pi-half pulse, we have to choose this omega times t equal to pi over 2. And that's just a convention. But you don't have to choose that. And so we have to multiply now this electric field with its 2 contributions with the dipole moment. And what we observe is that we get e to the I, and we have now omega atom plus phi evaluated at Zi and t, describing the transition from the ground to the excited state plus hc. So these are 2 terms. Yes? Excuse me? No, everything is just written as operators. I might just omit sometimes this head. Yes.
Maybe you can repeat the questions.
I'm sorry. Yes. Okay. Then
just realized otherwise
it's not on the Zoom. Okay, I will do that. Yeah. Okay. If there are other further questions, not. It's omega times t. Yes. Sorry. Of course. And then the other terms would be e to the I omega atom times t minus phi Zi and t plus hc. Okay, now we have those 4 terms just multiplied out. And at this point, we have to discuss a little bit what I did before, because those first 2 terms, let's say these 2 here, oh no, that's pretty dark, is it? Oh no, I think you can read it. Just dark on my screen. What you observe here is the following. You have your 2 levels, 2-level atom, and it describes this excitation. The photon h bar k is coming, and the whole thing gets a kick. And of course, the inverse process. However, now these guys back here, can you still read it? No. These guys back here, those describe the process where the atom is in the ground state and gets excited and a photon is emitted. The matrix element is missing. Yeah, exactly. So sorry. Yeah, exactly. So I just need to include that. But that's also going from the ground state to the excited state. It's the same matrix element. So what you observe now, something very weird. I emit a photon and I excite the atom at the same time. But that, of course, is well, when we look at this exponent, we see a little bit more what's happening. We now say that the phase phi at z in the interaction picture in T plus, no, the other way around, minus and plus omega atom times T is the following. I have VL, this offset phase. I have KZ. Now I have to use this definition plus P hat times K over M plus or minus omega atom. Yeah, I think I'm mixing up the plus and minuses here. Plus or minus omega atom minus omega times T plus K times alpha minus G times T squared over 2. What I've done is now I've used this Z in the interaction picture and plugged that into the phase. And we see now a few things arising. First of all, we observe that here you have the acceleration of gravity and this chirping. And what you can see is that you can get rid of that effect if you equate both of them. That means you're basically accelerating the atom or chirping the frequency to just counterbalance the acceleration that is felt by the atom. That's the first thing that you see. The second thing is that you see that you have here either the sum or the difference of two optical or possibly optical frequencies. You have omega of the light and you have omega of the atom. And it arises with the sum and with the difference. And now, of course, energy conservation is in some sense only fulfilled if there is a minus between the two of them. So it's omega atom minus omega. That reflects energy conservation. On very short timescales, you don't have to follow that. But we are working on sufficiently long timescales. Or in other words, you can apply also some systemized way to just get rid of those fast oscillating terms, those terms where you have a minus omega atom minus omega, where they basically add up and not the difference. They introduce a different time scale. And if that time scale is larger than all the other time scales relevant in our experiment, it kind of averages out. And for that reason, we now perform this, you can remove those fast oscillating terms consistently. And we will now perform something that is called the rotating wave approximation, where we drop the fast oscillating term. That's called rotating wave approximation. Okay, and if we do that, we find a nice wave of the Hamiltonian where we only have h bar in this interaction picture, which is h bar omega Rabi over 2 times e to the I omega atom times t plus phi in the interaction picture, of course, operator, times the excitation plus the inverse process. Okay, and that's now what we're going to work with. I said that we want to identify somehow this resonances and that we want to say or see also explicitly this momentum kick. And we do a trick for that, but that's okay. I think I missed something, but that's fine. Okay, so what are the resonances that we can see? And we can read off all the resonances from this Hamiltonian. And for that, we use Baker-Campbell-Hausdorff. I'll just write it out once. Yeah. yeah, so effectively, and we will see that effectively later if I have time, think in terms of a Dyson expansion, okay? Think in terms of Dyson expansion is just having a perturbative expansion of your time evolution operator. So we say that the time evolution, at first nothing happens, and then you have the integral in time over our Hamiltonian, and then you have higher orders, okay? Now, if you integrate in time, and your Hamiltonian is something like e to the h bar omega Rabi over 2 times 1 plus e to the I, and I just call it delta, okay? And you integrate over that, you observe directly that there is a time scale, and the time scale is given by this Rabi frequency divided by this oscillation frequency. So you have to look at the relevant time scales, and here are only two time scales of relevance. The one of this energy, the coupling strength, and the one of this detuning. And if you say that this year and this year, the ratio is very small, you can neglect these terms. Okay? Good. Yes?
Explain again why a photon is emitted when the atom is excited.
Yeah. So I basically read that in this description, you have to read it off whether K is plus K or minus K, because we don't have the notion of photons in this direction because it's a classical field. If we were to perform the same calculation with operators, annihilation operators and creation operators in Fock space, so if you have something like A acting on N is equal to square root N minus 1, that would replace one electric field amplitude, if you like, and a dagger acting on a Fock state is equal to n plus 1, n plus 1. That would be the Hermitian conjugate part of our electric field. And then you would can apply it in. And here you see that's absorption because it reduces the number of photon, and that's emission. It increases the number of photons. Okay? I'm sorry, I'm still forgetting to repeat the questions. Yeah. Okay. Okay, so now we use Baker-Campbell-Hausdorff and to identify this momentum kick. And you're all familiar with Baker-Campbell-Hausdorff, I guess, after this lecture. So what we will see is the following, and it's just a relation that we will use. So it's e to the, and now we have two operators A plus B. And this relation says that it's e to the A times e to the B times e to the minus commutator A B divided by 2 if higher order commutators vanish. And so on. Okay? In that case, you can now apply Baker-Campbell-Hausdorff and identify now this momentum kick. So what we are doing is we say that our A is e to the ikz. That's fine. But now when you look at this phase, and I expressed it up here, you see that it still depends on a momentum operator. So what we have to do is, in order to just separate this momentum kick, we know e to the ikz is the momentum kick. We still have this Doppler detuning. We will see that later. So we say that B is just I times P times K times T over M. And now the question is, what's the commutator between those two? And that the commutator, of course, is now I squared, K squared over M times Z and P. And here we just use the canonical commutation relations and just find that we have now minus I H bar times K squared times, forgot T, times T over M. And we still have to divide that by 2. And so if we do that, what we observe is, in this interaction picture, H bar omega Rabi over 2. And then we have e to the I phi naught plus kz. That's my momentum kick. And then we have a time-dependent oscillation, which is e to the I omega atom plus p times k over m plus h bar k squared over 2m minus omega times t times e to the I k alpha minus g over 2 times t squared times the excitation plus the inverse process. Okay, and that's now put everything in here. And now we are effectively done. So what we observe now is the following. We observe now, and similar to what Wolf did with his magnetic field, that's exactly what we've done now with the electric field as well. This here is the momentum kick. This here is the detuning. And now it depends on the velocity where you are. We observe a Doppler detuning. And this here is a chirping mismatch. And of course, Wolf already pointed that out earlier. Yes. Chirp mismatch. No, I never said trap. It's just my accent. And Wolf also was right, because he said earlier this morning, theorists are lazy, and I'm now being lazy as well. Or I don't like to do difficult calculations. Now, of course, this can be, in fact, this can be solved exactly, but we're not going to do that. What we are doing now is make our life easier. And what's making it difficult is that this Hamiltonian depends on time. Because we cannot, now solving the Schrödinger equation is difficult. If we want to calculate the time evolution operator, you have to take time ordering into account, and that's getting a big mess. So let's not do that. Let's just think about ways how to get rid of all those time dependencies. Now, the easy one is the following. Everybody in the lab is doing a great job. That means the chirping rate is exactly like gravity. By that, we get rid of this quadratic term in the phase. So perfect chirping. And by this perfect chirping, so alpha is equal to g, we get rid of this quadratic term. And we are always, so in principle, if all the rest can be neglected, we are always on resonance. We don't drop out of resonance during the interaction with the light. The second part is this momentum-dependent detuning. And let's study that closer. And for that, we look at the gained energy during absorption. Okay? And what's the gained energy during absorption? First of all, the atom is now excited, so it has potential energy gained, and it has gained energy h bar omega atom. Okay, that's easy. But what is all the other energy that it has gained? Yes. So alpha is, so what the question was, what's alpha depending on? Alpha is effectively just an experimental parameter. You just have an, well, now I need to say, let's say AOM or something like that, or I don't know how yeah, I don't know exactly how it's been run, but you have something that modulates your frequency, and the frequency is chirped, and that's a knob that you can tune in your experiment. Okay? Now, so you have the omega atom. Then you have the kinetic energy after absorption. And the kinetic energy after absorption is P plus h bar k, because you transferred momentum divided by 2m. But that's, of course, not the gained energy during absorption. So I have to subtract the initial kinetic energy over 2m. And I multiply that out. I have h bar omega atom plus h bar pk over m plus h bar times h bar k squared over 2m. And that is h bar omega atom plus something I call Doppler detuning that depends on momentum. So p times k times over m is just the Doppler detuning. You can also argue using the Doppler effect plus omega k. And that is the kinetic energy scale h bar k squared over 2m that is associated with the energy transfer. And this is exactly what the detuning is all up to. So you now say that if the gained energy during this absorption is equal to the frequency of light, you observe a resonant transition. And that includes both the internal energy and the kinetic energy gained during that. And here we observe a momentum-dependent Doppler detuning. So let's also write down that this is a Doppler detuning. I just need to find my mouse. Yeah, there you go. So this would be Doppler. And that would be the recoil, so-called recoil frequency. Okay.
But you observe the resonant line for which?
Exactly. So I will write that down as well. So we have a resonant transition. We have a resonant transition if we have omega atom plus nu of p resonant. I call this the resonant momentum plus omega k is equal to omega light. In this case, the exponential vanishes and we're done. The only problem is at this point, I just said, okay, there's one momentum and I can have this time dependence up there vanish for this one particular momentum. And yes, that's true. The problem is if you go into the lab and prepare a sample, you have a finite width of your imposition of your atoms, and by that also a finite width in momentum. That implies that only one momentum of your cloud of atoms can be resonant. The other ones, even for a single atom, because it has a finite width, is detuned. That means you have detuned Rabi oscillations, but now what we are assuming is that the resonance width, so that the detuning or this momentum width is sufficiently narrow. So we assume that the wave packet momentum width is narrower than effectively our recoil frequency. So we now assume and that's why it's so also important to, for example, work with Bose-Einstein condensates and not a thermal cloud of atoms, because you have a thermal momentum distribution and then you have everything there and you can just address a few atoms in this respect. So we assume that narrow of width delta p, and we assume that nu k of delta p of this width is much smaller than the Rabi frequency. And in this case, we can neglect also the time dependence up there that I just mentioned. You can also base this argument on Fourier arguments, make this assumption by just saying, okay, but the width of this resonance really depends on the duration of your pulse, but we'll get to that later. So if that is the case, if we assume that, we can just, the only remaining part is effectively this Hamiltonian here. And this is the time-independent time-independent Hamiltonian H in this interaction picture is just h bar omega Rabi divided by 2 times e to the I phi L plus k z momentum transfer times the excitation. going from ground to the excited state plus the inverse process. So exciting, transferring momentum, and the inverse process. Okay, good. Any questions so far? What we did was now a little bit different than what you see in standard textbooks, because we took the center of mass motion into account and really identified why on Earth it's necessary to have chirping. If you have free atoms, if they're in a trap, of course, that's not a problem because they're not being accelerated. And why you need a sufficiently narrow momentum distribution to address all of them. We saw that we transfer atom upon photon absorption. So this is kind of like the difference to, let's say, the more or less standard treatment. Okay, let's go to the next little section that we're talking about, and that is now Rabi oscillations. And who knows Rabi oscillations already? Just raise your hand. Okay, that's very good because I don't need to just solve this Schrödinger equation for that. It's time independent. It's not a problem. We can just take the operator exponential of that. If you have questions, please ask me during lunch. So we will both miss lunch, but at least I can also make that little derivation. So what we now calculate is the just matrix exponential of this Hamiltonian. And that is the time evolution operator. Yeah. And so the solution is S, and I have an index omega times tau, or omega Rabi equal tau is equal to e to the minus I over h bar times hi, of course, an operator, times tau. And if we do that, we find that it's cosine omega Rabi times tau over 2 times the identity acting on the external degrees of freedom times the identity acting on the internal degrees of freedom minus I sine omega Rabi times tau, over 2 times e to the I phi L plus kz times the excitation plus hc. Okay? Yes, please. So, I mean, there are a few things actually, and I will show also experiments in gravimetry later on. In gravimetry, this is important not only, so okay, think of it differently. Effectively, when you have a clock, what do? You somehow try to match your laser frequency to the atomic transition. And by that, you perform the Ramsey sequence, for example, with one particular frequency setting of your laser. Then you say, okay, it doesn't really work. There is still a detuning. Then I change my frequency. So effectively, what you're doing, you're performing runs of different experiments with different light frequencies and find a null fringe, a fringe where basically both of them match, where you don't have detuning. What you do now in atom interferometry is effectively the same. We will later on see also that the laser phase, and that's also important here, is also imprinted on the atoms. So you need chirping. And what you do is you effectively match your chirping rate to gravity to find a null fringe. So if you were not chirping, the atoms would drop out of resonance and you could hardly excite the atom, depending on the duration of your pulse, of course. But let's assume we are working in a regime where you have sufficiently long pulses. At least you will see that you don't diffract all the atoms anymore. And so when you go to, so you basically adjust your chirping rate in such a way that you just observe good diffraction. And the same is true for your interference signal. You adjust your interference signal in such a way that you effectively match your chirping rate to gravity. And that's done experimentally. And that's actually what you read off a gravimeter, if you like. That's the observable, the chirp. That's why I like chirping, and that's why I included it here also here, because that's effectively, in some sense, in gravimetry, that's the observable, not in a quantum mechanical way, but that's actually what you read off your machine.
Just follow up on what the young lady said. She says, hey, look at this Hamiltonian. There is nothing left of the chirp or of the acceleration.
Yes, if you, exactly.
The chirp compensates the acceleration.
Exactly.
And in other words, you see the equivalence principle. You see the equivalence principle because you see that in a freely falling system, when you change the electric field, it's the same situation.
Exactly.
There would have been no gravitation.
Think of the atom. The atom is dropping. Yeah, the atom is dropping and accelerating. And I effectively counteract that by accelerating my optical lattice. We just have one beam now, so, but let's say also one beam is a lattice. So effectively, we accelerate the so that the light drops at the same rate as the atom, effectively. Yes.
Maybe the question was sort of, you lost all your signal right now. You matched perfectly.
Yeah, so if there is a slight detuning, you can also solve that. I just didn't want to do it, but in principle, you can.
There's no signal whatsoever.
Yeah, because you take out gravity completely, right?
Yes, exactly.
So if you don't do that perfectly, then you get your signal.
Exactly. And what you're trying to do is you're trying to find an alpha fringe. I will come back to that tomorrow. Yes. Yes. Okay, good. So also, and that's effectively connected to the measurement we are talking about tomorrow, is that we have here this initial phase of the light that enters. And that's also become important because upon photon absorption, we observe that the phase is imprinted. And if the phase changes in a sequence of pulses, we will see also this difference in phases. And that's actually the signal that we're trying to match to gravity. So I just want to say that it's because it's important. We also observe that the initial phase of light enters. Okay, good. So let's just, because you're all familiar with Rabi oscillations, I don't plot the sine function and a cosine function or squared functions. But let's just assume that we now have an initial state and we now have a state psi that comes out of such a Rabi oscillation where we have this operator acting on an initial state, and we just say that the atom is initially at P, let's say, resonance times the ground state. And what you observe now, if you multiply that out, those matrices, what you observe is that you first of all have something like cosine omega Rabi tau over 2 times P resonance times the ground state minus I sine omega Rabi tau over 2. And now that's the important part. You have e to the I phi L. The phase is imprinted. And now you observe P resonance plus H bar K. Oh, I think there's something I completely forgot on the previous slide when we were discussing the resonance condition. Plus excited. I will just do that right now. When we were talking here about this resonance condition, what did we do? We have here the energy, and we have here momentum. Okay, and so we have a ground state, and the kinetic energy is like a parabola in the ground state. And the excited state is up here. So this would be the ground state, and this is the excited state. So upon absorption, what you do is you excite from here to here, you transfer momentum, and the momentum is H bar K, okay? And you transfer energy H bar omega of the light. And of course, if you have a different momentum that is not resonance, I just use the very same arrow back here, it doesn't work. And that's effectively what we did in this energy conservation discussion. And that's actually also what we observe in the equations. That's exactly this contribution. Okay, so now, Rabi oscillations. Now we see that we get a periodic excitation and momentum transfer. And we can now choose the duration of our pulse or the intensity of our pulse, because the Rabi frequency depends on the electric field and by that on the intensity, so that we just have a superposition. Now, there we go. So what do we now observe? For a pi-half pulse, both sine and cosine are 1 over square root of 2. So what we observe is now P resonance times ground state minus I e to the I phi laser times P resonance plus h bar k times the excited state divided by square root of 2. And now coming back to the picture that we originally had. So this is position, and this is time, and I have the atom in the ground state. And now I interact with such a light pulse. And what I observe is now a superposition. So 50% do have momentum, and momentum applies that they move in a different direction upon time evolution. And 50% just go straight. And this here is ground state, and this here is the excited state. And if you look at that state, you observe that you get entanglement between internal and external degrees of freedom. Whenever the atom is excited, it has absorbed a photon, it has gained momentum. That's just a Bell state. Yes?
Why is time going to the left?
Because we write operators always from the left. You will see that after the break. Yeah, and actually, it's not. No, I can't take credit for that. You always multiply with left, like the semi-group property of time evolution operators.
Yeah, that's right.
Okay, let's just finish this up. This is a beam splitter. You now see that with such a pi-half pulse, you can split up the beam. And the same is true, of course, if we choose pi. Pi implies that the cosine is vanishing and the sine is equal to unity. So we have minus I times e to the I phi L times P resonance plus h bar k times the excited thing. So whenever the atom changes its momentum, it gets a phase, and yeah, and that's it. And so for this mirror pulse, we observe the following. So we also start here in the ground state, but then we interact with the light field. So here, this is time and this is time. We interact with that light field. We transfer all population to the excited field and the atom, excited state, and the atom moves in that direction. So now we have beam splitters and we have mirrors. And let's just, because we will need that later, because now we have optical elements, we can build a Mach-10 interferometer, beam splitter, mirror, beam splitter, and we can interfere stuff. And just that we have those operators, so we just introduce a mirror operator. Yes?
At this point, we cannot
Exactly, but I'm not interfering yet. We will add two beam splitters, and then you will observe that you get a superposition of two arms ending in one exit of the interferometer. That's what we will see this afternoon. So the mirror operator in this particular picture, this is something that I put under the rug, but you feel free to ask me afterwards. S pi L, because it still depends on the laser phase, is equal to minus I times e to the I, phi L plus kz times E G plus e to the minus I phi L plus kz times GE. That's what we call a mirror operator. Just do this interaction. And the next thing is a beam splitter operator. And that's where we have a pi half pulse is equal to, and now this is a little bit, more difficult to write down, 1 over square root of 2, but it's just the identity of the external and internal degrees of freedom plus or minus I. And now we just have e to the I phi L plus kz times EG plus e to the minus I phi L plus kz times GE. Okay. And we can now work with that. And we still have 10 minutes. Now, what am I going to do with 10 minutes? First of all, I just want to, and I wanted to do that explicitly, but of course, I think it's better to make this thorough. There are also higher order photon transitions. Yes, please, please ask a question first. Yes. Yeah, so you have the superposition of the atom. So it's exactly the state that's on the very top here. If you look up here, you have the atom up here, and you have a superposition of probability 1/2 of being in the ground state and continuing with the same momentum, and a probability of being in the excited state and having gained momentum. And that's a superposition. So each and every single atom is, if you like, simultaneously in 2 momenta. And if you propagate that, we're going to talk about that after the break, or after Professor Schleich's lecture, they're going to separate because they have different momenta. Only the excited state. Yeah. Whenever the atom is in the excited state, it will have a kick and fly in some direction. Okay, good. Okay, so now to wrap this up, there are also higher order transitions. There are other diffraction mechanisms. And one of them is Raman diffraction. So the point is, if you, for example, think about your favorite atom, and you just work, for example, with rubidium, and you just say, okay, let's just drive transitions between 2 hyperfine states. That works perfectly. I just need a microwave and so on. If you have a microwave, think about the transferred momentum. That's not a lot. So what you actually want, you want to transfer a lot of momentum. So why not just moving to optical transitions? Well, first of all, you have to think about the atom at hand, in that case, rubidium. But you could also say, yeah, maybe I do have a clock atom, so I can drive a clock transition. But of course, that's very difficult. So and then of course, you have an optical clock transition, you transfer a lot of momentum. So what you can do is you can play tricks. You can play tricks, and originally I was planning on giving a short derivation of that, or at least motivation. But what you do is you have your atom sitting somewhere, you have it with some momentum, let's say it's resonant, and you have a blue light field coming from the left with some frequency, so K blue and omega blue, and you have a red detuned, and the colors are, of course, not literal colors, K red minus K red in the opposite direction, omega red. So what does that imply? Let's not go through the math. Let's just go through energy conservation. So let's again now, and let's now assume, and that's also the thing, we assume now that these two fields couple a three-level system. We now have an auxiliary state, A, we have a ground state, and we have an excited state. And these are now the excited and ground state you use, for example, hyperfine states in rubidium. And now what we do is we use this blue light field to couple to the auxiliary state up here. And we use a no coupling to the excited state. And we use the red light field also to couple the excited state to that. And now, effectively, everything comes out in second order perturbation theory. You can already see what happens. And actually, I would have really liked to show that because it's also cool given the lattices that we see and so on, because you can also derive how star shifts, how potentials also for the traps are shaped by just detuned interactions. So now let's draw these three states and their kinetic energies up here. So this is the ancilla state, this is the excited state, and this is the ground state. This is the momentum, and this is their energy. So what happens is that we couple with the blue field and absorb a photon to go up here. And now the atom is excited, but it's highly detuned, so it doesn't want to stay there. We can also think in terms of this rotating wave approximation business. Nothing happens if you just have a single photon transition because it averages out because of those frequency scales. However, if you add another transition, you can go back down to the excited state. And because now the momentum is going into an opposite direction, upon stimulated emission, it emits another photon. It emits a photon in the opposite direction, so gets yet again momentum transfer. So what happens is that you transfer momentum up here. And effectively, you can drive Rabi oscillations between two states that are not optically separated, or that are, for example, hyperfine states, and long-lived and well-behaved and everything, but still transfer momentum. And the transferred momentum in this case is, of course, and the calculation then afterwards, if you have an effective description, works the same. It's K blue plus K red. And we can play another trick. We can do the very same thing. And I know it's now maybe a little bit abstract, but maybe some of you have already seen figures like that. We can do the same thing without changing the internal state. And that's called Bragg diffraction. And here we just have one state that is detuned. And we have again counter-propagating light fields. We excite, transfer momentum. We emit and transfer momentum. And so we can drive Rabi oscillations also between two momenta, but the atom is in the very same state. And that's also good because different internal states see different things, and that's not always good. But not to mention, there are atom interferometer experiments with clock transitions. And for example, they're very good, or also estimated to be very good for gravitational wave detection and so on. But most atom interferometer setups nowadays, light pulse atom interferometer setups for that matter, work with Raman or Bragg diffraction. The problem with Bragg diffraction is that in principle, a process like this here could also happen. So, you just absorb a red photon and emit a blue photon. However, that doesn't really fulfill energy conservation. And then you can play, again, tricks with different frequencies to consistently remove those states. Okay, everybody is nodding and nobody's asking questions. Yeah.
But you didn't feel standard Bragg diffraction, so you were just transferring, you're changing momentum of the internal state.
So effectively what happens? You have a blue light field. Photon is coming from the left. You have the atom in the ground state. The blue photon is absorbed, the atom is excited and gets a kick. Now, because the light field was so much detuned, the atom really doesn't want to stay in its excited state. It's sometimes called a virtual state. Now you have a red light field coming from the opposite direction, and it stimulates emission. And the atom is very happy to lose its energy. So the atom emits a red photon in that direction, so it gets yet another kick in that. And by this emission, it goes back to the ground states and has gained momentum. That's the process of Bragg diffraction. And the same would, yes? With Bragg diffraction, it's just a superposition of two momenta. You don't have to play with internal states. We will do that later on, always with internal states for just pedagogical reasons, because it's easier. But in principle, you get a superposition of P resonance plus P resonance plus H bar K divided by root 2, and here is whatever, minus I. Okay? Good. If there are no further questions, I'm not sure if I promised you, but I will, or threatened you. But I just was prepared a few slides with experiments. So first of all, Rabi oscillations. We were talking about these Rabi oscillations. Most of you have seen them. This is Rabi oscillations of a lattice of different atoms. And the excitation probability is plotted for each atom at each position in a lattice, just having a microlens array or something. And there is a Gaussian beam that drives these Rabi oscillations. And this Gaussian beam, of course, has different intensities at different locations. And so what you observe is where you have a high intensity, there's fast Rabi oscillations. Where you have low intensity of your beam that comes on top, you have slower Rabi oscillations. And so that really tells you that the Rabi frequency is connected to the intensity of the beam with one side. Yes? This is the excitation probability, the probability of finding the atom in the excited state. And that is a single atom sitting at one particular, it's a microlens array at one particular position. Velocity selectivity. I was just saying, okay, we talked about resonant momenta, but there's only one resonant momentum. So what happened here is this is also the first atomic Bragg experiment. You have the atom sitting here, and because they do have a momentum distribution, only specific momenta are addressed by that pulse. This here is a pi pulse, and what you observe is that some population at rest is cut out and diffracted, whereas the other stuff is not addressed. Exactly, and then of course I messed up my slides here. Exactly, but that was just serving that. Also, if you ever, so it actually was supposed to blend in. But what you observe is now, if you average over the whole distribution, that's now. That means we have a different Rabi oscillation for a different momentum. So one momentum is resonant, the other ones are not resonant. And you see here the time evolution. And if you have now a momentum distribution, you basically have to multiply it and average over that. And here, looking at this Rabi oscillation, you see that those oscillations are damped. And they are damped because of velocity selectivity, because you have to average over this momentum distribution, and then the oscillation just damps out, because for each momentum, you have a different amplitude and a different frequency. And finally, Bragg diffraction, you can also stitch them together. I didn't draw that on my slides here, but you effectively can just make higher order processes. What you can do is you can make one transition that's off resonant, but then add another transition that makes it resonant again. And you can also play with time scales and then find effective Rabi oscillations between the two. And that's the lower figure there. And what you observe is that the frequency now scales differently. of course, because now you're working with a different system. But that also connects to what Jason will talk about later on this week, because he's interested in transferring multiple momenta. We will see tomorrow that the sensitivity of an atom interferometer for inertial sensing depends on the transferred momentum. So the more momentum I transfer, the better. And that means that this higher order diffraction also can be one way, or transferring multiple momenta can be a way to make your sensor more susceptible to the signal. And I think you're all hungry. You're welcome to ask questions concerning those slides, or afterwards I will just linger around here. And we'll see. I think Wolfgang Schleich is going to give a lecture right after lunch, and after that we will follow up on what we developed this morning to describe a whole interferometer and actually see different arms emerging that interfere. Thanks.
So lunch will be on the village square. So there's there's a restaurant called Ligatron, which is if you go just out of here.
We'll go to them, so they will.
Okay, we'll all go together.
Yeah.
So yeah, back here at 3 o'clock sharp. Don't think we have coffee just before that, but we can coffee culture.
Thank you.
You can send a coffee somewhere, and see you then.